Good morning students, welcome to physics online class. Today first we are going to recall what you learned already in the previous class, okay? What you observe from this picture, when the sunlight enters into the room through the window. See what you can see here, the path of light rays, okay? The path of light is visible to our eyes, okay? So this effect is called Tyndall effect. Okay. Now we can recall the definition of Tyndall scattering. Scattering of light rays by the colloidal particles in the colloidal solution. Scattering of light rays by the colloidal particles in the colloidal solution. What do you mean by colloidal particles? Colloid means is a microscopically small substance equally dispersed throughout another material. Okay. So microscopically small substance equally dispersed throughout another material. Example, milk is the example of colloidal solution. See here, milk contains calcium, vitamins, minerals, okay, but it is equally dispersed throughout all the materials. Okay, so this is the example of colloidal solution. Some more example we can see here. Ice cream is the example of colloidal solution. Muddy water, smoke, etc. Okay, so these are the examples of the colloidal particles, okay, or colloidal solution. Okay. Next we learned Raman scattering. Is it? Who discovered this? 1928, Sir C.V. Raman. Okay, he discovered this fact. So what he discovered, when a parallel beam of monochromatic light passes through gas or liquid or transparent solid, a part of light rays are scattered. Listen, when a parallel beam of monochromatic light. What do you mean by this monochromatic? The light rays which consisting of a single wavelength, okay, or single frequency, okay, that is called as the monochromatic light. Okay, it is passed through gas, liquid or transparent solid. We can see the scattered beam of light. Listen here, the scattered light contains additional frequencies other than that of the incident frequency is called as the Raman scattering or Raman effect. Listen, the scattered light contains additional frequencies other than that of the incident frequency. Okay, so that is called as what? Raman scattering or Raman effect. Just observe this picture, we can see the different lines here, isn't it? Okay, different spectral lines we are seeing here. So listen here, this blue color arrow line denotes the incident ray of light. Okay, incident ray of light. Here this line denotes the scattered beam of light. Okay, so here just these two lines will have the same frequency. Okay, the lines will have same frequency as that of the incident frequency or incident light, that is called as the Rayleigh line. Okay. So the line having the frequencies equal to the frequency of the incident light is called as the Rayleigh line. Now you can see here the frequency is just lower than that of the incident frequency. Okay, the frequency of the scattered beam of light is lower than that of the incident frequency. That is called as the Stokes lines. Okay, that line is called as the Stokes line. Now here see the frequency of the scattered beam of light is higher than the incident frequency. Okay, the frequency of the scattered beam of light is higher than the incident frequency. That is called as the anti-Stokes lines. Okay, these two lines are called as the Raman line and this is the Rayleigh line. Okay. Next we learned about the lenses. Okay, what do you mean by lenses? Is optically transparent medium bounded by two spherical refracting surfaces or one plane and one spherical surface. Listen, optically transparent medium. Two sides also maybe the spherical refracting surface will be there. Otherwise, one side plane surface, another one side spherical surface is there. Okay, that is called as the lenses. Okay, then what are the two types of lenses we studied? Have you remember? Okay, yes, there is two type of lenses. What are they? Convex lenses and concave lenses. Okay, first we studied about the convex lens. Okay, convex or biconvex lens. Okay, what do you mean by convex or biconcave lens? Okay, convex lens. Okay, see here, just observe this picture. Listen, it is thicker at the center than at the edges. Okay, convex lenses are thicker at the center. Okay, center portion it is thicker than at the edges. Okay, from that we can identify that is the convex lens. Okay, the refracting surface is just bulged outwards. Okay, and when a beam of light is passing through it, it is converged to a particular point. Okay, when a beam of light rays are passes through the convex lens, all the light rays will meet in one particular point. Okay, so these lenses are called as the converging lenses. Okay, convex lenses are called as the converging lens. Okay, just observe this picture. This is the convex lens. Okay, listen here. When the parallel beam of light rays are allowed to pass through the convex lens, at a particular point all the rays will meet here. Okay, converged here. Okay, so this point is called as the focal point or the principal focus. Okay, for a convex lens, the parallel beam of light rays allowed to pass through the lens. After refraction, it will meet in one particular point. Okay, so this point is called as the principal focus, and this principal focus to this center of length is called as the focal length. Okay, so all the light rays are converging here, so it is called as the converging lens. The next type of lens is called as the concave or biconcave lenses. Okay, what's that? Concave or biconcave lens. Okay, so listen this picture. So this concave lenses are thinner at the center than at the edges. Okay, they are thinner at the center. Okay, just opposite to the convex lens. Okay, they are thinner at the center than at the edges. Okay, see here, when a parallel beam of light passing through it, what will happen here? It will diverge or the light rays are spread out. Okay, so it is called as the diverging lens. Concave lens are called as the diverging lens. Why it's called so? The parallel beam of light passing through it, it is diverged or the light rays will spread out. Okay, so it is called as the diverging lens. Okay, just observe this picture here. When the parallel beam of light rays are allowed to pass through a concave lens, see here, this is the refracted ray. After refraction, it will diverge back. Okay, like this it will diverge back and it will meet at this point. Okay, so here this is the principal focus. Okay, the parallel rays after refraction, it will diverge back and it will meet here at the point. Okay, so this is the principal focus. So it is called as the diverging lens. Okay, it is called as the diverging lens. Have you understand? So next we studied about the image formation of lenses. Okay, so before that we studied certain rules. Have you remember? There is 3 rules. Rules are there. Okay, so the first rule, what the first rule states that when a ray of light is allowed to pass through the optic center of a convex lens. Okay, when the ray of light is allowed to pass through the optic center. Optic center means you all know that, isn't it? It is the center part of the lens. Okay, that is denoted by the letter O. Okay, when the ray of light is allowed to pass through the optic center, after refraction also it will continue the same path. Okay, without any deviation, it will go to the straight line. Okay, so this is the first rule. Okay, when the ray of light allowed to pass through the optic center, after refraction also without any deviation it will continue the same path. Okay, so this is the first rule. So listen here, this line denotes what is the line? Principal axis. Okay, so here this line is the principal axis. Okay, when the first rule states that when the ray of light allowed to pass through a optic center without any deviation, it will go to the same path. Okay, so this is the first rule. See, the first rule, it is applicable for both the convex and concave lens. Now we can see the second rule. When the parallel beam of light rays is allowed to pass through the convex lens, after refraction what will happen? It will meet on the principal focus. Okay, so this point is called as the principal focus. Okay, when the parallel beam of light is passed through the convex lens, after refraction it will pass through the principal focus. Okay, for a concave lens what will happen? After refraction, when the parallel beam of light is passed through the concave lens, so this is the refracted ray. After refraction, it will diverge back and it will meet at the principal focus. Okay, so this is the divergent lens. Okay, so after refraction it will diverge back and meet here. Okay, so this point is the principal focus. See here, in this lenses both the sides the principal focus is here. Okay, so this side we have to take f1 and this refracting surface it is f2. Okay, and we learned what is the third rule we learned. Have you remember? Okay, when a ray of light is directed towards the principal focus of a convex lens, after refraction it will be getting parallel to the principal axis. Okay, see here, these two lines are parallel. Okay, first itself it will be directed towards the principal focus, means after refraction it will be what? Parallel to the principal axis. Okay, for a concave lens what will happen? When the ray of light is directed towards the principal focus, after refraction the lines are parallel to the principal axis. Okay, these are the three rules we learnt already. Okay, then we learn the refraction through the convex lens, isn't it? Depending upon the position of the object, where is the image is formed. Okay, so in that first case we studied, if the object is at infinity, okay, it is far away from the lens, means where is the image is formed. Listen here. So these are the parallel beam of light rays coming from the object. The object is at infinity, okay, far away from the lens. Okay, so all the parallel rays according to the second rule, where it will meet on the principal focus. Okay, the parallel beam of light after refraction it will meet on the principal focus. Okay, so and here listen. So this axis is called as the principal axis, and this points. Okay, so this is the point f1 and this is f2, and both the sides we have to mention 2f1 and 2f2. Okay, so this 2f1 it is also called as the center of curvature. It is denoted by c1, and similarly for this refracting surface here we have to mention this point c2. Okay, this is 2f2. Okay, so the light rays are coming from the object. After that it will be meet in one particular point. So here only image is formed. Okay, so this point only the image is forming. Okay, so the image formed at the focus. Okay, what about the size of the object? It is much smaller than the object. The object is much smaller than the object. Okay, so then what about the nature? Nature is real and inverted image. Okay, the image is real image and it is a inverted image. Okay, if you are focusing the tree, we can get the image is the inverted image of the tree we can get here. Okay, so image is formed at the focus and size is much smaller than the object. And what about the nature? Real and inverted. Okay, the second one, if the object is beyond C or greater than the 2f position, means where we can get the image. Listen here. See, this is the convex lens, this is the optic center, this is the principal focus, both the sides f1 and f2 have to mention, then 2f1, okay, from this point to 2f1, that is center of curvature c1, and here the center of curvature c2. Okay, now what is the condition? Object we have to place beyond C. Beyond C means, see here, this is the position of the center of curvature. Beyond C means here, this position we have to keep the object. Okay, let us consider AB be the object. Okay, AB be the object. This is the object. Okay, now from the object to the parallel beam of light rays are coming from the object. According to the rule, where it will go, it will meet on the principal focus. Okay, it will goes to the principal focus. Okay, then according to the first rule, the rays are passing through the optic center. Okay, optic center means without any deviation it will goes to the same path. Okay, so now the two refracted rays, where it is meeting between the focus and the center of curvature. So here only image is formed. Okay, the image is formed here. What type of image this one? Inverted image. Okay, the inverted image is formed between F and the center of curvature. Listen here. The image position is between F2 and 2F2. Okay, or between the focus and the center of curvature. Okay, size of the image just observed, almost it will be same size. Okay, and the nature of this image is real and inverted. Okay, nature of the image is real and inverted. Next, in the third case, if the object position is at C, if you are placing the object at the center of curvature. Listen this picture. So this is the convex lens, this line principal axis, this is the optic center. For where we are going to place the object? At the center of curvature. Okay, at the 2F1 position. So here we are placing the object. So AB be the object. See the first ray parallel to the principal axis. The rays coming from the objects are parallel to the principal axis. According to the rule, where it will go? It will goes to the principal focus. Okay. So this is the refracted ray line. Then the next ray, it is passing through the optic center. Okay. Optic center means without any deviation, it will be goes to the same path. Now where the two rays are meeting? So this point. Okay. So this point means correctly this side, the center of curvature. Okay. So here only the inverted image is formed. Okay. So object position is at center of curvature means the image position also the next side of the center of curvature. Okay. Listen here. The image formed at the center of curvature. Okay. What about the size of the image? Same size. Okay. Comparing with the object, is almost the same size of the object. And what about the nature? It is a real and inverted image. Okay. Have you all understand? The real and inverted image. Okay. Next position, the object is placed between F and C. Between the focus and the center of curvature means where we will get the image. Listen here. So, convex lens. So, we are placing the object between the focus and the center of curvature. Okay. So, here only are placing the object. Okay. So, A, B be the object. Object is placed between F and the center of curvature. Okay. So, where we can get the image here? See the parallel beam of light rays. First you have to draw the parallel beam of light rays. According to the rule, it will pass to the principal focus. Okay. And the next ray passing through the optic center, it will goes to the same path without any deviation. Okay. Now the two rays are meeting in this point. Okay. So here only the image is formed. Okay. The image is formed beyond the center of curvature or beyond the 2F2 position. The image is formed. Okay. The two rays are meeting here. No. So here only the image is formed. Okay. So the image position is beyond C. Okay, the image position is beyond the center of curvature. Size of the image, just look at this picture. It is bigger than the object. Okay, bigger than the object. And nature is real and inverted. Almost for all the convex lenses will get real and inverted image only. Okay. Next, the object position is at the focus. If you are keeping the object at the focus means where we can get the image. Listen here. So this is the focus point. Okay. So now we are going to place the object here. Okay. At the focus. Okay. So AB be the object. We are placing at the focus. First the parallel rays where it will meet on the principal focus. Okay. And the rays passing through the optic center. So without any deviation, it is going like this. So just observe this picture where anywhere that two rays are meeting here. No. Okay. So the two rays are not meeting anywhere near to the lens. Okay. So the two rays, it will be what meet that is far away from the lens. Okay. So the image position will be at infinity. Okay. Where is the image formed? At infinity. Okay. So object position is at focus means the image position is at infinity. Okay. So object position is at the focus means image is at infinity. And if you are looking the size, it will be much larger than the object. Okay. Comparing with the object, it is a very big size if the image is formed. Okay. And the nature of the image is the same. Okay. Real and inverted. Okay. Next one, the object position is between F and optical center. The object position is between the focus and optical center O means where we can get the image. Okay. Just listen here. So here between the focus and this optic center we are keeping the object. The object position is between the focus and the optic center. See first the parallel rays. So after refraction it will pass through the principal focus. Okay. And the optic center, the rays passing through the optic center, it will goes like this. And here this condition alone, these two rays will diverge back and it will meet here. Okay, the two refracted rays, it will meet at this back of this lens and it will be what here this point it will be meeting. So here the image is formed. Okay. So here this A dash B dash denotes the image. Okay. So here this case alone we are getting the image is the virtual image. It's not a real image. It's a virtual image we are getting, and the image is the erect image. Erect means it's not a inverted image. Okay. So except all this except this case, remaining everything are getting that real and inverted image. This case alone we are getting what image? What type of image? Virtual image. Virtual means it's a not real image. Okay. So object position is between the focus and the optic center. We are getting the images between the images. Where is the image is formed? So between the F and the center of curvature. Okay, between the focus and the center of curvature we are getting the image. Okay, and the size of the image is larger than the object. What about the size? It is larger than the object. Okay, this is the object, but we are getting the image somewhat larger than the object. Okay, and what about the nature? It's a virtual image. Okay, same side, which side we are keeping the object, same side we are getting the image. So it is a virtual image and erect image. Okay, not inverted, the same as like the object, the image is there. So okay, it is a erect image. Okay. So next we learned some of the applications of the convex lens. Is it? The first application, the convex lens is used as the camera lens. Okay, the convex lens is used as the camera lens. Okay. Next, this lens is used as the magnifying lens. Okay, so this is the magnifying lens. What is the use of this magnifying lens? We can see the small things. Okay, we can see by using this magnifying lens. Okay. So next application, it is used in the microscope. Okay. The convex lens is used in the microscope. Okay. Next, what is this? This is the telescope. Okay. In the telescope also, what lens is used? The convex lens is used. Okay. This is the slide projector. In the slide projector also, the convex lens is used. Okay. So the convex lens is used in the telescope, microscope, and the slide projectors also. Okay. The last application, it is used to treat the defect of hypermetropia. See, some of the defects are there in the vision of our eyes, isn't it? In that hypermetropia, it is one of the defect. Okay, that defect is corrected by using what type of lens? Convex lens. Okay, so these are the applications of the convex lens. Next, we learn the refractions of a concave lens. Okay. So depending upon the object position, where is the image is formed? The first position, the object is at infinity. Okay, so this is the concave lens. We are placing the object at far away from the lens, where is the image is formed. Okay, so from the object to the parallel rays are coming from the object. If it is a concave lens, means the refracted rays are spread like this, isn't it? So this is the refracted ray. After refraction, the rays will diverge. Okay, the parallel beam of light after refraction will diverge back and it will meet here at the focus. Okay, the parallel rays after refraction, it will diverge back and it will meet at the point. Okay, so here only the image is formed. Okay, object is at infinity means the image position is at the focus. Okay, the image formed at the focus. And what about the size? It is much smaller than the object. Okay, comparing with the object size, it is very, very small. Okay, and nature is a virtual image. Okay, we can get the virtual. It is not a virtual image we can get. Okay, and it's a erect image. Okay, it is a virtual and a erect image. Next one, the object is at anywhere on the principal axis. Okay, so if you are keeping the object at anywhere on the principal axis, where is the image is formed? Okay, listen here. So this is the principal axis. The object here we are placing the object. Okay, at any one position we are placing the object. Okay, A, B, B the object. See the first the parallel rays according to the rule. This is the refracted ray. After that it will diverge back and it will meet with this principal focus. Okay, then from the object to the light rays are passing through the optic center. Okay, so without any deviation it will go straight. So these two refracted rays are meeting this particular point. Okay, so here only the image is formed. Okay, so the image is formed between the optic center and the focus. Okay, so these 2 points between here only the image is formed. Okay, so this is the position of the image. Okay, so let us take A dash and B dash be the position of the image. Okay, so where is the image is formed? Between the optic center and the focus. Okay, object is at anywhere on the principal axis. The image is formed between the optic center and the focus. The size is smaller than the object. See, compare the size. This is the object, this is the image. Okay, it is smaller than the object, and nature is a virtual and erect image. Okay, and we learned what is that? Application of a concave lenses. Okay, can you guess who is here? He is the inventor of telescope. Okay, Galileo Galilei. Okay, he only first introduced the telescope. Listen here, this is the Galilean telescope. So in the Galilean telescope, the concave lens he used. Okay, as the eye lens. Okay, so the eye lens he used as the concave lens. Okay, so this is the Galilean telescope. Okay, so in that concave lens is used. Listen here, next application of a concave lens is the wide angle spy hole in doors. Okay, so the concave lens is used as the wide angle spy hole. Okay, in doors. Okay, so in the door, the center of this position, they will fix that concave lens. Okay, so what is the applications of this one? Whoever be standing outside, we can see from this hole inside. Okay, so easily we can understand. Okay, who is standing outside. Okay, so it will be used as the wide angle spy hole in the doors. Okay, see from the spy hole, from the inside too, we can, if you are looking there, the person who is standing outside, easily we can observe. Okay, that is the use of the concave lens. It is fixed in the doors. Okay, if you are sitting and watching inside, who is standing there, easily we can see through that hole. Okay, see next what we studied. It is used to treat the defect of myopia. Okay, the myopic persons, they are using what type of lens? Concave lens. Okay, so concave lens is used to treat the defect of myopia. Okay, so these are the applications of the concave lenses. Next we are going to learn what is lens formula. Okay, what is the use of lens formula? What is lens formula? See, the lens formula, it gives the relation between the object distance u and the image distance v and the focal length. You all know that what is object distance and what is image distance and the focal length. See, what is object distance? Listen here. So the optic center to from which place we are keeping the object. Okay, in between that distance is called as the object distance. Okay, what do you mean by image distance? From the optic center to the image, where the image is formed. Okay, that is denoted by V. This is the image distance. Okay, and here what is meant by focal length? The distance between the optic center and the principal focus. Okay, in between that distance is called as the focal length. Okay, so the lens formula, it tells the relation between the object distance, image distance and the focal length. So this is the formula. What's the formula? 1 by f is equal to 1 by v minus 1 by u. What's the lens formula? 1 by f is equal to 1 by v minus 1 by u. Here f denotes focal length, v denotes image distance and u denotes the object distance. Okay. Next we are going to learn the sign convention or the Cartesian sign convention. Okay, while doing the experiment, we had to follow certain convention, sign convention, where we had to put the positive sign and where we had to put the negative sign, etc. Okay, all these it will be considered as the Cartesian sign convention. Okay, so according to this, what is the first one, first rule? Okay, so always we have to place the object. Okay, object always to be placed to the left side of the lens. Okay, so whatever the lens we are using, concave or convex, okay, object is always to be the left side. Okay, so this is the left side of the lens. Okay, always all objects should be in the left side. Okay, so this is the first sign convention. Okay, so object should be always in the left side of the lens. Okay, where you have to place the object? In the left side of the lens. Okay, and the second one is all distance measured from the optical center. Whatever the distance we are measuring, we should measure from the optic center. Okay, for example, object distance if we are measuring means from the optic center to here. Okay, so like this direction we should measure. If we are measuring the image distance, maybe the image is formed this side. Okay, so then we have to measure from the optic center to here. Okay, so all the distance measured from the optic center. So what is the second rule? All distance measured from the optical center. Okay. The first one is object always should be in the left side of the lens. The second one is all distance measured from the optical center. Okay. The third rule is distance measured in the same direction of incident light means we have to take that is positive symbol. Okay. Distance measured in the same direction of incident light. What's that meaning? Distance measured same. This is the direction of the incident light. Okay, so whatever distance we are measuring, like this direction of this incident light. Okay, this is the direction of the incident light. Okay, so from this direction whatever distance if you are measuring, that one we have to take as the positive. Okay, for example, if you want to here the image is formed maybe, so we will measure from here to here. Okay, so this is the direction of the incident light, so this it will be taken as positive. Okay, all distance, okay, distance measured in the same direction of incident light means we have to take as positive. Next is just opposite to this, distance measured against the direction of incident light. What are the distance we are measuring against the direction of the incident light means that will be taken as negative. Listen here, suppose we want to measure the object distance. Okay, object distance from where to where we have to measure? From the optic center to here. Okay, so this is the direction. So this direction is just opposite to the direction of the incident light. Okay, this is the incident light direction. Okay, so for this just opposite to this direction means this will be taken as what? Negative sign. Okay, distance measured against the direction of the incident light, so it should be taken as negative. Okay, that is the next point. Okay, distance measured against the direction of incident light means taken as negative. Okay, the next point, distance measured upward. Okay, what are the distance we are measuring? Upward. Okay, listen here, this direction. Okay, see, distance measured upward from the principal axis. This is the principal axis. Okay, so what are the distance if you are measuring upward? Upward means so here. So maybe here this is the object, isn't it? Object distance. Object is above the principal axis, upward. So this it will be taken as what? Positive. Okay, so distance measured upward from the principal focus, principal axis means that is taken as what? Positive. Okay, so if you want to measure the length of the object, we have to taken this is the positive symbol. Okay, distance measured upward means okay, positive. Next last point, distance measured downward, that is perpendicular to the principal axis, is taken as negative. What are the distance if you are measuring in the downward direction from the principal axis? Okay, so that should be taken as negative symbol. Okay, listen here. So this is the image. Okay, the image is formed below the principal axis. Okay, downward direction we are measuring. So this will be taken as negative. Okay, so above the perpendicular axis of the principal axis is known as positive. So below any distance if you are measuring, or length of the image or length of the object, whatever may be, measuring the downward direction means it should be taken as negative. Okay, have you all understand? What's the first point? Cartesian sign convention, object should be always to the left side of the lens. What's the second point? All distance measured from the optical center. And the third one is distance measured in the same direction of incident light means positive. And the distance measured against the direction of incident light means negative. And the distance measured upward, okay, above the perpendicular axis means that is positive. Below the downward direction, okay, it will be taken as negative. These are the Cartesian sign conventions. Okay, next definition. We are going to learn what is magnification of a lens. Okay, the magnification of a lens can be represented by the letter M. What is magnification? The ratio of the height of the image to the height of the object. We are comparing the two height. Okay, height of the image and the height of the object. Okay, that is denote magnification. So magnification m is equal to height of the image by height of the object. Okay, the height of the image represent h dash, height of the object represent h. Okay, and also it is related to distance of the object and distance of the image. Okay, we have to mention the object distance and image distance also. So m is equal to distance of image or image distance by object distance. Okay, image distance is v and the object distance is what? U. Okay, so this is called magnification. Magnification, what do you mean by magnification? Ratio of the height of the image to the height of the object. M is equal to height of the image by height of the object. Now listen, if the value of magnification, if you are getting, that value is greater than 1 means we are getting the enlarged image. Okay, size of the image is very large. Magnification value is greater than 1. Okay, we are getting enlarged image. And the magnification is less than 1 means we are getting the diminished image. Okay, so based on this value we can say it is an enlarged image or it is a diminished image. Have you all understand? See, we learned already what is lens formula. Now we are going to learn lens maker's formula. Okay, those who are making the lens, what are the things they have to note it. Okay, so lens maker's formula. See, lenses are, you all know that lenses are a transparent material. Okay, so all the lenses, all the transparent material have the refractive index. Okay, so refractive index and all you learned already. So lenses are the transparent material, it will have the refractive index. Okay, and the lens formula, you know, it is relates the focal length, object distance and the image distance. Okay, for a lens maker's formula we need the extra one. What is that? Radius of curvature also we record. Okay, for a makers of any lens, of radius of curvature of the lens is required. Radius of curvature means what? What is radius of curvature? Listen here. So this is the spherical surface. Okay, all the lenses, it will be forming from the part of the sphere. Okay, the sphere has the center. Okay, the sphere has the center. So from here to here, this position is called as the radius. Okay, this position is called as the radius. Okay, so this radius of curvature value we required for making the lenses. Okay, so the radius of curvature is important for making lens. So it gives the relation of radius of curvature r and the refractive index mu and the focal length. So the lens formula noted by 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. What is lens maker's formula? Mu minus 1 into 1 by r1 minus 1 by r2. Here you all know that f denotes the focal length. F denotes what? Focal length. And mu denotes the refractive index. Mu denotes what? Refractive index. Mu denotes the refractive index. Okay, and this r1 and r2 be the radius of curvature of the two sides. Okay, two spherical surfaces there now. For one surface, let us take r1 radius of curvature, and another surface it is r2. Okay, this is the lens maker's formula. Next important question, what do you mean by power of a lens? What do you mean by power of a lens? Okay, the ability to converge or diverge the light rays depend upon the focal length. Okay, that is called as the power of a lens. The ability to converge, because convex lens, converging lens, concave lens or diverging lens. So ability to converge or diverge the light rays depends upon the focal length. Okay, so the ability of a lens is called as the power of a lens. Okay, ability to converge or it will diverge. Okay, that ability is called as the power of a lens. Okay, but numerically we can define what is power of a lens. Okay, it is a numerically defined as reciprocal of its focal length. Okay, power of a lens is reciprocal of the focal length. See, the power of a lens denoted by the letter P. P is equal to 1 by f. Okay, because the ability of convergence or divergence depends upon what? Focal length. See, so power of a lens is equal to 1 by f. The reciprocal of focal length is called as the power of a lens. P is equal to 1 by f. And the SI unit of this power of a lens is diopter. What's the SI unit of power of a lens? Diopter. Okay, so for one word questions and all, they will ask what's the SI unit of power of a lens. So what we can mention? Diopter. Okay, so it can be represent the symbol D. It can be represented the symbol D. Okay. So diopter, the SI unit of power of a lens is diopter. It can be represented the letter D. Okay. And now we can define what is 1 diopter. See, 1 diopter is equal to 1 meter power minus 1. How this meter power minus 1 came? See, the unit of the focal length, we all know that meter. Okay, unit of the focal length is meter. So 1 by f. 1 by f means 1 by meter. So power of a lens is 1 by focal length. Okay, if you are taking this meter here, meter power minus 1. So 1 diopter is equal to 1 meter power minus 1. Okay, 1 diopter is equal to 1 meter power minus 1. Okay, f, the unit of this focal length is meter. Okay, power is equal to 1 by f. So 1 by meter. So it is equal to meter power minus 1. So 1 diopter is equal to 1 meter power minus 1. Then for a convex lens, the value of this power of lens, it will be positive. Okay. For a convex lens, power of a lens you have to take positive, and for a concave lens, the power of a lens is negative. Okay. For concave lens, the power of a lens is negative. Okay. The last one, we are going to learn what is the difference between convex and concave lenses. Okay. You all know about the convex and concave lenses. Now we are going to learn the difference. First, convex lens. Okay. But depending upon the size, how to identify it is thicker in the middle than at the edges. Concave means thinner in the middle than at the edges. So, it's the first point. Convex lenses are thicker in the middle than at the edges, and concave lenses are thinner in the middle than at the edges. Okay. And it is a converging lens. Convex lenses are called as the converging lens, and concave lenses are called as the diverging lens. Okay. And the third point, mostly convex lenses produces real images. Okay. Always it will be producing a real image. But concave lenses forming visual images. Okay. Mostly produces what type of image? Visual image. Okay. It is not a real image. Okay. And the last one, the convex lens is used to treat the defect of hypermetropia. Okay. The long-sightedness, hypermetropia. And the concave lens is used to treat myopia. Convex lens used to treat hypermetropia, and concave lens is used to treat myopia. Okay. Short-sightedness. Okay. Students, today you have to learn and write this question. Okay, difference between convex and concave lenses. Okay, and also we have to learn and write Cartesian sign convention. Okay, these two questions we have to learn and write in the note. Okay, thank you students.